Hello students, welcome back. Let us resume our discussion on power series methods. Let's begin with a review on analytic functions. A real function is said to be analytic around t0 if it can be written as a power series expansion centered at t0 like this. This expression is valid in an open interval centered at t0, which we call the interval of convergence. And the radius of that interval is called the radius of convergence. Basically, it goes like this. If the distance between t and the center of the interval t0 is less than the radius, that is, if t is selected inside that interval, then this power series is valid. It converges absolutely. If the distance is greater than the radius, or equivalently speaking, if t is selected outside of this interval of convergence, then this diverges. What if the distance is equal to r? Luckily, we don't have to consider it here in this course because we take the derivative all the time, so we don't have to consider the endpoint. All the intervals we consider here in this course are open intervals. In Calculus 2, you have to consider the endpoints, but not here. Okay, the next topic, the fundamental theorem. Basically, it's the existence and the uniqueness. Let's begin with the standard form of a linear ODE with variable coefficients, like this, and assume that all the functions here are analytic. Then, given initial condition, we have a unique solution like this. The solution exists, and it takes this form. So the existence part sets the direction. We can assume y of t takes this form, take the derivative, second derivative, third derivative, and so on, using term by term, put everything in there, and then compare all those powers and get the recursive relationship between CNs, and so on and so forth. Yes, that's the essence of the power series method. And that's valid because the solution exists, and it takes this form. So the existence part gives us the direction. The uniqueness part, on the other hand, gives us the validity. There's one and only solution, so if you take this power series method and if you successfully identify Cn and get this expression, then that is the solution. Because there's nothing else, there's only one solution. Whatever method you use, if you find it, that's the solution. So combine both of them and we call it the fundamental theorem. The existence gives you the direction, and the uniqueness gives you the validity. The proof, on the other hand, is way out of the scope. So let's just move on. We need it for the foundation, but as for the proof, maybe I'll do it in some other course like real analysis 2 or differential equation 2. Not here, not in this course. Okay, next topic, the singularity issue. Given homogeneous linear ODE like this, and suppose that all the coefficient functions, b0, b1, b2, b3, and so on, they're all analytic at t0, then we call that t0 an ordinary point, or a non-singular point. Otherwise, we call it singular point. That is, there is at least one coefficient function that is not analytic. In that case, we call t0 a singular point. We studied the power series method centered at ordinary points previously, and in that case, we can determine the radius of convergence like this. It's the distance between the center of the power series, t0, and the nearest singularity. And the nearest singularity here is in complex plane. So, for example, if the center of power series is 0, and the nearest singularity is 2 plus 3i, in that case, you can use Pythagorean to find out the distance, and that distance is the radius of convergence. Okay, I don't think we have to review index shifting. Okay, so much for review, and let's go to the new topic. Regular singular points. Sounds like an oxymoron, because usually regular means non-singular, and singular means irregular, but in this case, we have really strange term, regular singular point. What do you mean by that? Sorry, but I cannot change it. It's too late. This term was invented far before I was born, so I cannot really say anything about it. It's just an oxymoron, but at the same time, it's a specific term that you just have to get used to it. It's a singular point, that is, one or more coefficient functions is non-analytic at t0, yet you can multiply by t minus t0 to something power to make it analytic. Or equivalently, you can decompose like this, where a0, a1, a2, all these are analytic. And are they equivalent? Yes. Here I can start from here, and then divide everything by t minus t naught to the nth power. So we get this. Let me expand the font a little bit so that you can see these fractions and powers a little bit more clearly here. And then k power was already there. And then divide by the nth power. So we get n minus k power down there. And flip it to the other side. What do you get? We get this. ak equals to that. And that's nothing more than this one here. So ak is analytic, means this thing is analytic. So those two expressions are actually equivalent. Whether you use from here to there, or you use this one directly, it doesn't matter which way you do. Which method do I prefer? I like the original one. Okay, just by looking at the definition, it's really hard to see. So let's look at an example here. Prove that this ODE has a regular singular point at t equals 0. Let me open up this. Okay, for this problem, it's easier to apply the second. So that's the original problem here. And you can rewrite it in terms of some a times t minus t0 in that form. So this is t squared times y double prime. You can write this t to the first power times sine of t times that. And this is t to the 0 power times that, okay? And let me emphasize these. So 0 power, first power, second power is in this form. 0 power here, first power, and then the second power. This one is written in terms of arbitrary order, but you can clearly see. Another way to do it is to start from here, the original, and then divide each by t squared. So divide by t squared. We don't have anything there. T squared, and then this one. And then we have a bit of a simplification here. Let me expand the font so that you can see this thing better. And then you just get just one power. And we have the second power. Do you see that? Maybe you can see it better if I have one more expression here, 0 power there. So we have 0 power, first power, second power in the denominator versus 0 power, first power, second power in the numerator in backward order. Either way, you can see that this thing has a regular singular point at t equals to 0. Whether I use this expression in denominator, which I personally like better, or this expression, either way it works out fine. Our textbook author does both. Okay, how about the next example? Find all singularities. Which one is regular? Okay. So it sounds like there gotta be more than one singularities in this problem. Okay, let's find those out. And then let's divide everything by t squared minus 4 squared. So t squared minus 4 squared minus 4 squared. A bit bigger font. And let's simplify a little bit further. This one can be simplified into t plus 2 squared, t minus 2 squared. How's that? How do you like this? I guess one more simplification is in order. This t minus 2, and then that cancel out. And then we have this form. Now we have the standard form. And which one is regular? Do you see it? We have two singularities. We see t equals to 2 and t equals negative 2. I see two of them. That's when the denominator hits 0. So that's one, and that's another. And then that's associated to red. And this one is associated to blue. Make sense? Now, which one is regular? Which is regular? Maybe you can see things a little bit better if I write like this. Oh, wait a minute, this is not squared. 0 power. So that's red and that's blue. Okay, all right. There was 1, so I just artificially created appropriate powers here, 0 power. Now for blue, you can clearly see this is a regular singularity. 0 power, first power, second power. Do you see? 0, 1, 2 in denominator. And how about red? 0, 2, 2. No, doesn't work because of this. So for blue, it's regular. 0, 1, 2. Look at the denominator. And for red, no, it's not regular. 0, 2, 2. It doesn't work. So we have a regular singular point at t equals to 2. The other singularity is not regular. See the criterion? In the denominator, 0 power, first power, second power. Here, for red, we have 0 power, second power, and middle one, that's no good. So we went through regular singular points. And the next topic here is the power series method around the regular singular points. Basically, we are trying this. Previously, we studied this kind of power series. Take the derivative. So, and then we have n minus 1 And then from here, we take another derivative. Okay, I could take third derivative and fourth derivative if necessary, but in practice, you're not going to see that kind of complicated problem. The second order is as hard as it will get. Put everything there, and then do your computation, and then determine Cn. That is the power series method that we used to employ. Now, for regular singular points, by the way, ordinary point. At ordinary points, we used to do these. For regular singular points, we need extra R power here, which I'm highlighting in green. And that results in n plus R power. And when you take the derivative, they're going to be affected. So basically, we're going to get this. So this is n plus R power. Come on, plus R power. And taking the derivative from here, I'm going to get n plus R power, and this is n plus R minus 1. And the second derivative, n plus R, n plus R, and then n plus R minus 1, and then n plus R minus 2. If you apply a power rule, these are the derivatives. And then you have to put these into the original equation, probably this form, and then work those out and determine coefficients. That's the second power series method, or frobenius method. This series is called frobenius series, by the way. Now, what's the difference between the frobenius series and the usual power series at ordinary points? And we don't have this odd power, so we have n minus 1, n minus 2, and also here we have n times n minus 1. We have something different, r here, so n plus r and n plus r minus 1. A little bit of difference there. That's the first difference. Second difference is the starting point. Here, this n equals to 0 starting point can be changed into starting at n equals to 1 freely. And I can change this into either n equals to 0 or n equals to 1 or n equals to 2, no difference. Because if I plug in n equals to 0 here, 0 times something, this entire thing drops out. So whether I start from 1 or 0, it makes no difference. Same here. If I plug in n equals to 0 or n equals to 1, this entire thing is just 0. So whether I start from n equal to 0, 1, or 2 made no difference. This time they do make difference, so I cannot change this. And that's gonna affect the index shifting a little bit. Exactly how? Well, that and many other things will be discussed in a separate video.